In this video, I'm going to talk about probabilities. Now, what is a probability? Well, for our purposes, probability forms the basis of inferential statistics. So far, we've only spoken about descriptive statistics. Now we can start the inferential part of statistics. You can think of a probability as the likelihood of observing something. Right? If something has a high likelihood of happening, it has a high probability. If it has a low likelihood of happening, then it has a low probability. Now, probabilities are based on something called the law of large numbers, and the law of large numbers basically says as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. Now, for example, suppose we have a fair coin. Now, by a fair coin, I mean one that's not weighted. It won't favor one side over the other. If we flip a fair coin 1,000 times and observe how many times heads occur, okay, we can look at this and say, well, what if on flip 1, so we say on flip 1, we get a tail. Right, so on flip 1, we get tails. Alright, that means that 0 out of 1 flip is heads. Now, maybe on flip 2, we get heads. Alright, so what does that mean? That means that 1 out of 2 flips is heads. And what if on flip 3, we also get heads? Then I can say 2 out of 3 of those flips is heads. Alright, now the idea is if we keep going, I'll just put a dot, dot, dot. If we keep going and we continue this process with the fair coin, you'll notice that the proportion of heads is approaching 1/2. Alright? And that's the idea of the law of large numbers. The longer you do something, the more the theoretical probability will approach the actual probability will approach the theoretical probability. So let's start with some definitions here. All right, we have the definition of a sample space, and a sample space, we use the letter S, of a probability experiment is the collection of all possible outcomes. All right, so every possible outcome of the experiment is an element of the sample space. An event is simply any collection of outcomes of a probability experiment. So think of that as a subset of the sample space. So let's look at an experiment. All right, so right here I have an experiment. We've got a fair die. Again, just like a fair coin, it's not weighted on any one side. All right, so we roll a fair 6-sided die. What would the sample space be? Well, it would be the set of all possible outcomes. So the set of all possible outcomes would be you could roll a 1, a 2, a 3, a 4, a 5, or a 6. Alright, so this would be our sample space. Now suppose from that sample space we take an event, and that event is that I roll an even number. Right, what would that event consist of? Well, all the even numbers from the sample space. So 2, 4, and 6. So you would think of this as your event. Right. Now, probabilities are very specific. They follow a set of rules, properties. Right. So first of all, notation-wise, right, the probability of an event E is noted as P of E. It's function notation. That's what we use. And there are 4 basic properties that define a probability. The first one is that a probability is going to be a fraction between and including 0 and 1. All right, so a probability is between 0 and 1. If that probability, let's look at the endpoints. All right, if that probability equals 0, right, the probability of something equaling 0 means that the event won't happen. Right, E won't ever happen. If the probability of an event is 1, well, then the event must happen. All right, everything else between 0 and 1 is a likelihood. All right, how likely is event E to happen? All right. The more likely it is, the closer to 1 the probability will be. The less likely it is, the closer to 0 the probability will be. All right. Now this last property says that if we have a sample space that consists of, let's see, that consists of some number of events, we'll say n events. So I'll just use, or n elements. That should be a 2. All right, so go all the way up to en. All right, so if we have that sample space, then the sum of all the probabilities for each of those possible outcomes, all right, we add them all up here, all the way up to P of n, PE of n, will equal 1. All right, so the sum of all the probability of all the possible outcomes is going to equal 1. All right. When we look at a sample space, when we look at the probabilities of all of the elements in a sample space, we get something called, what our book calls a probability model, what most of the rest of the world calls a probability distribution. Okay. So probability distribution is just a list of all possible outcomes and their probabilities. All right, now I mentioned in class about the M&Ms. So I have a distribution here for the color of plain M&Ms. All right, and what you'll see here is brown has a probability of 0.13, yellow has a probability of 0.14, red has a probability of 0.13, and so on all the way down. Right. So what we end up with here is, first of all, to define a probability distribution. All right, we know it's the list of all possible outcomes and their probabilities, but the properties that make a probability distribution is entirely contained in the probability column. I don't care what my descriptive column is. It makes no difference what my descriptive column is. What defines a probability distribution is the probabilities. Okay, so for a probability distribution, I have to have the two basic properties of probabilities. All right, so all my probabilities have to be between 0 and 1. And the sum, and I'm going to do it this way, of all the probabilities of every element in my probability distribution has to equal 1. Alright, so if I add up this column, okay, if we add up this column, we do indeed get 1, and I can see that each one of my probabilities is between 0 and 1. So this satisfies all the requirements of being a probability distribution. Alright, it's important to remember that it's only the probability column that defines the probability distribution, not the other. Right? So the next question becomes, how do we calculate probabilities? Alright, there's two methods. The first method, which is called the empirical method, is based on observation, and this is something we've been doing pretty much all along. Alright, you take a survey and you look at your survey data. You observe some sort of real-world phenomenon, or you do some sort of experiment, and you gather data yourself. Okay. Now, the empirical method is based on calculating relative frequencies, which again is something we've been doing all along. I can look at some data that we saw back at the beginning of the semester, and that is our 25 Army recruits who were given a blood test. All right, we had all the blood types here, and we have the frequencies of those blood types here. So I can calculate the relative frequencies for all these. Right? The relative, I'll use the same relative frequencies, right, by simply doing, right, there were 25 of them, right, 5 over 25, 7 over 25, 9 over 25, and 4 over 25. Now I can look at these as fractions if I want to, but probabilities, we tend to go either with the fraction or with the decimal form, so I'm going to write both of them down here. All right, 7 over 25 is 0.28. 9 over 25 is 0.36. And 4 over 25 is 0.16. All right, and you can verify all the important stuff. This does end up adding up to 1. Okay. And you can think of these also as percents. Right, so 20%, 28%, 36%, 16%. Any one of these three is an acceptable way to write probabilities. So now if I ask, what is the probability that one of these Army recruits selected at random has blood type B? All right, I go over to blood type B, calculate the relative frequency in this particular sample, and it's 0.28. So 0.28 would be the probability, or 28%, that one of these recruits has blood type B. Right? So that's one method, again, based on experimentation. The other method, which is referred to as the classical method, right, is more theoretical. All right? So where the empirical method is an approximation based on an actual probability experiment, the classical method relies on counting techniques, does not require the actual experiment to be performed. Now, it does require something called equally likely outcomes. And equally likely outcomes just means that every outcome has the same probability of occurring. All right, so no matter how many outcomes the experiment has, every single outcome has the same probability of occurring. So in a sample space with n equally likely outcomes, the probability of an event occurring would be the number of ways the event can occur over the total number of outcomes in the sample space. So if we use a capital N function-wise to represent number of, this would be the number of events, the number of ways the events can occur over the total number in the sample space. Okay. So let's look at an actual example of this, and we can use something that we just talked about, which was rolling a die. Alright, I don't want to actually have to roll a die 100 times or 1,000 times or 1,000,000 times for my law of large numbers to take effect. Okay, I want to say what's the probability of rolling an even number in the sense of classical probabilities. So if you recall, we had a sample space which was this. And we had our event, which was rolling an even number, which was this. Alright, so that means the number of elements in my sample space is 6, right? 1, 2, 3, 4, 5, 6. And the number of elements in my event is 2, 4, 6, so that's 3. So the probability that I roll an even number is going to be what? It's going to be the number of events, the number of elements in my event over the number of elements in my sample space, which would be 3 over 6. Alright, and if you're going to write probabilities as a fraction, you always reduce it to lowest term, so that would be 1/2. Alright, also 0.5 would be fine for that too. Okay, so calculating probabilities, you've got two possibilities. Alright, you've got the empirical method, which is based on experimentation, and you've got the classical method, which is based on which is just based on the equally likely events. Okay.